Okay. So, therefore, we can now write the current voltage characteristics of the MOSFET for two conditions: when VDS is less than VGS minus VT, which is the linear operation. Even though this equation is non-linear, it is linear when VDS is very, very small, because you can ignore this term. And when VDS is greater than or equal to VGS minus VT, we have saturation operation, and this becomes the current voltage characteristics. You see that this current does not depend on VDS, it is independent of VDS. Okay. So, if you were to plot these two together, you would end up with a plot like this. You will find that if you plot VDS versus IDS, you see this is a parabola. In fact, initially in the early regions it is linear, but it is in fact a parabola, right. So, it is something that would do this, but just when VDS is equal to VGS minus VT, the current saturates and it does not depend on VDS anymore. Okay, so, that is what these two equations telling you. So, these two equations are a good enough first order jump as to what the current voltage characteristics in a MOSFET are. But then we need one more detail, okay, which is, does VDS really not impact the saturation mode current? Okay. So, you think about it. So, let us take let us say we have we have just hit the VDS, let us say VDS is equal to VGS minus VT. At this point, the channel, only this channel potential here, only that region has got the channel potential being equal to VGS minus VT, and therefore, my Qn, which is Cox into VGS minus VT minus Vc, is now 0, right. It is only that point which has got 0 electrons. Everywhere else the channel potential is less than VGS minus VT, because the maximum value it could take is the VDS equal to VGS minus VT. But let us say we increase VGS further and we keep increasing VDS, we keep increasing the drain to source voltage. So, the drain to source voltage is now much greater than VGS minus VT, which means that if you look at the channel potential, if you were to probe Vc, there is a point here where Vc has already become equal to VGS minus VT, and beyond this Vc is greater than VGS minus VT, and at this point my Vc is equal to VDS, which is of course greater than VGS minus VT. So, it is the pinch off point now relocates to a different region, and as I keep increasing VDS, the pinch off point will start drifting towards the source side, right. So, therefore, we are actually altering this resistor combination. So, if I told you there is a resistor beyond pinch off and there is a resistor below pinch off, by actually moving the pinch off point I am changing the values of these resistances. So, technically speaking, my VDS must influence my saturation mode current, but that is not what the equations told us. Okay. So, what we are going to do is we are going to add an empirical correction to the current voltage characteristics. Now, this fact that the VDS, that when a transistor is in saturation, the fact that the VDS can actually influence the current voltage characteristics is something called as channel length modulation, okay, which means that the effective channel length, okay, is being, the behavior of the channel is being modulated by the VDS, even though the device is in saturation. Now, this is a very important phenomena because it directly impacts your circuit design, particularly if you want to build amplifiers. Channel length modulation plays an important role in determining the gain, etc. Now, from the point of view of a circuit designer, this channel length modulation in a MOSFET has got a equivalence. If you remember, in the case of a BJT, we had the base width modulation, and the base width modulation was, you had your BJT, it was operating in active mode operation, and in active mode operation your VC was not supposed to influence the current a lot, but even then we saw that the VC does influence the current because the width of the base changes, because the depletion thicknesses change. and we saw that the current versus VCE did have a small trend even in active mode operation. It's exactly the same situation here. The physics is different, completely different, but from the point of view of a circuit designer, these two have the same impact. Okay. They determine the output impedance of your MOSFET or of the transistor BJT or MOSFET. So, the channel length modulation impacts the, it makes the VDS influence the drain current, not by too much, by a little, but it is important enough that it impacts the design of your amplifiers. So, now given these two equations, okay, so these are the current voltage characteristics of the MOSFET to the first order. Given these two equations, what do the plots look like? So, we have two plots. We have the drain to source current versus VGS, which is something called as the transfer characteristics of the MOSFET, and we have the drain to source current versus VDS, which is the output characteristics of the MOSFET. So, what do? We take the MOSFET. So, let us say I want to plot the transfer characteristics. We have the source, we have the drain, we have the gate. The transfer characteristics is IDS versus VGS. We set a value for the VDS, we set this, and then we sweep the VG and we measure the current, and then you change the VDS to a different value and again sweep the VG and measure the current. So, let us take this particular VDS. Okay, so, here the VDS is let us say 1 volt, and now you sweep the gate voltage, and as you sweep the gate voltage you find that the current increases. Now, shift the VDS to 2 volts, and now as you sweep the gate voltage you get a new curve and so on. So, you develop the transfer characteristics of the MOSFET, and you can go back here and you can actually see whether you can fit these models into the transfer characteristics. Now, for the output characteristics of the MOSFET, what do? We take the MOSFET, we fix our VGS, we say that okay, VGS is fixed, we fix this voltage and we sweep the VDS and you measure the current through the device. So, here let us take a particular value of VGS, and now we sweep the VDS and you trace this particular curve, and then you take another value of VGS and sweep the VDS and you get another characteristics. Now, this particular characteristics, both of them tell you a lot of things, but let us just look at this particular the output characteristics a little. When VDS is very small, you can see that the IDS and VDS relation are almost linear. So, that is the linear, here the MOSFET behaves like a resistor, but you can keep increasing. So, we have picked a certain value of VGS, is not it. So, let us say VDS keeps increasing, and let us say it reaches a point where the VDS is equal to VGS minus VT. So, let us say that is that point that corresponds to this x coordinate. So, till here the MOSFET is in the linear mode of operation, and beyond this point the MOSFET enters a saturation mode of operation. So, you can see that in saturation the VDS does not change the current a lot, the current is more or less constant, but still because of channel length modulation there is some small increase in the current. So, if you look at it, the current does increase a little with increasing VDS, but not by too much, okay. And that is sort of empirically added in by this little linear relation, where this lambda is something called the channel length modulation parameter. Okay. Now, if somebody were to ask you as to what is the resistance of the MOSFET or the small signal resistance of the MOSFET, what is the answer? Okay. So, let us think of the MOSFET, let us take the MOSFET, and what we want to know is what is this resistance, the small signal resistance here. So, in other words, we want to find out what is dVds by dIds, which is if I have a small signal fluctuation in the drain to source voltage, how does the current in the MOSFET fluctuate. Okay. So, now this strongly depends on whether the MOSFET is in linear or in saturation. So, let us say that the MOSFET is in linear mode operation. So, what is dVds by dIds for a MOSFET in linear? So, if the MOSFET is in deep linear, let us ignore this term, because VDS is, let us say VDS is much smaller than VGS minus VT. So, we can just ignore this term. So, what we are asking is what is for a MOSFET in linear, what is dVds by mu W over L. So, d of IDS, which is mu W over L C ox into VGS minus VT into VDS. So, you just take this derivative and take the inverse. So, you calculate dIDS by dVds and take the inverse of that, and you will end up with the resistance being small signal resistance of the MOSFET in linear mode operation being 1 by mu Cox W over L into VGS minus VT. So, that is the small signal resistance of the MOSFET which is operating in linear mode operation. So, if you increase the mobility of the carriers, does the resistance go up or down? It definitely, it makes a lot of sense that it goes down. If you improve the field effect by increasing Cox, the resistance of the MOSFET goes down. If you make the channel width much larger than the channel length and increase the aspect ratio of the MOSFET, of course, the distance travelled by the electrons from the source to the drain decreases and the sheet charge area increases, and therefore, the channel length resistance will come down if you increase the aspect ratio. And if you increase the gate overdrive voltage, which is the gate to source voltage minus VT, if you increase that, definitely you have created more inversion, more electrons, and therefore, the resistance comes down. So, this is the resistance of the MOSFET in linear operation. Now, what about saturation? So, what is dVds by dIds in saturation? So, let us say the MOSFET does not have channel length modulation, let us ignore that. Okay. So, you have this. Now, since this current does not depend on, so let us write the linear equation first. Okay. Let us just keep it aside. So, that is 1 by mu Cox W over L into VGS minus VT, that is the linear small signal. Okay. Now, for saturation, we are using a saturation mode current, but we are not going to, we assume that it is an ideal MOSFET and there is no channel length modulation. So, what is this? Since there is no dependence on VDS in the current, this is infinite, okay, because dIDS by dVds now becomes 0. Okay. The current does not vary with the voltage, it becomes 0. We can vary this voltage as much as you want in saturation. Okay. So, let us say VDS increases in saturation is greater than VGS minus VT, and you increase or decrease this voltage as much as you want in this region. The current in this will never change, okay, it does not depend if there is no channel length modulation. So, the MOSFET behaves like a constant current source. You can change the voltage across it as much as you want, and it behaves like a constant current source, and in a constant current source the output impedance is infinite, and the MOSFET is telling you that it has got an infinite output impedance. But if you do include channel length modulation, okay, so if you do include this, then this is no longer infinite. You have a VDS term, and therefore, you will have a lambda into this particular parameter appearing in as the channel resistance. Okay, but ideally speaking, the small signal resistance of the MOSFET in saturation is very high, okay, and ideally infinite. So, if you look at these characteristics here, if you take the slope, you find that there is a resistance, it is a finite resistance, but here you see that there is no change in current irrespective of what the change in VDS is, and the resistance is infinite, the small signal resistance is infinite. Okay. We are not talking about what is VDS divided by IDS, because you do have a large enough IDS, and that is we are not talking about the large signal resistance, we are talking about the small signal resistance, which is if there is a fluctuation here, then what is the fluctuation in the current, and ideally it should be 0. Now, what do the transfer characteristics tell you? The transfer characteristics tell you that till a certain point there is no increase in current. Okay. So, we could define a threshold voltage somewhere. So, if you take a very low VDS, if VDS is much smaller than any VGS that you are applying, then the characteristics is almost linear, which is what is expected, it is almost like a straight line. And if you were to project the straight line all the way back, you would intercept the x axis at the point of Vt, that will be the threshold voltage. So, we will have a small module on parameter extraction where we can show how to use these characteristics to extract the parameters. But just to look at that, just to look at that point again, let us take the linear mode operation of the MOSFET. Right. So, here is the MOSFET in linear mode. So, you have IDS is, we will say it is deep linear where VDS is much smaller than VGS. So, you have mu L Cox into VGS minus Vt into VDS. So, now we are plotting the transfer characteristics. How does IDS depend on VGS? It is a straight line, as below Vt, as long as VGS is below Vt, the current is 0. We will develop finer models which will tell us exactly what the current should be, but for now it is 0 because there is no inversion layer, and after Vt the current should linearly increase. And what is the slope of this? The slope is simply mu WL Cox into VDS. So, that is the slope of the current voltage characteristics, the transfer characteristics when the MOSFET is in linear mode operation. And what is the x intercept of this characteristics? It will be Vt. So, you can work out and see what the x intercept of this characteristics is. Okay. So, this becomes a very useful method to extract both the mobility as well as the threshold voltage. So, it becomes a very powerful tool when you want to extract the parameters of a MOSFET.